Alright, attempt number 5 at our magnetism video. I guess I should spell this right, huh? Our magnetism video. Just overhead announcements that keep coming up and making it hard to hear. If anything comes up at this point, I'm not going to retry, so we'll just kind of grin and bear it and try and get through. So this video is going to be about magnets and about the relationship between magnetism and electricity. So the first question we have is, well, really, what is a magnet? And a magnet is just a material that attracts iron or substances that contain iron. And they have a north pole and a south pole. Always have a north pole and a south pole. There's 3 materials that we need to know about that can be made into magnets. They're iron, cobalt, and nickel. Elements number 26, 27, and 28 on the periodic table of elements. Now, I'll be talking a lot about iron, but the same really applies to cobalt and nickel in terms of creating magnets. So if we wanted to take a lump of iron and turn it into a magnet, there's something we need to understand. That's that in that material, iron, nickel, and cobalt, they have these areas called domains, which you can kind of think of as little magnets within the material, within the iron. Where, say, the pointy end of our magnet here, a pointy end of our arrow here would be, say, at the north end of a magnet, and the other end would be a south end of a magnet. But a normal just lump of iron, these are all pointing in different directions, so they're all kind of canceling each other out. This one's pointing down, this one's pointing up, they cancel each other out. This one's pointing to the right, this one's pointing to the left, they cancel each other out. But if we can get all those domains to align so they're all pointing the same way, now we can have a magnet. So this whole side, the north ends, all the pointy side of the arrows on over here, all the other side of the arrows are over here, so that's our south end. We've got a north end of a magnet, south end of a magnet. Now, there are lots of materials that don't contain domains, like rubber and plastic and wood and aluminum even. These don't contain domains, so we can't really turn them into magnets. That's why we're limited to just a few different materials. Now, magnets have an area, 3 different properties. They have 2 poles, north pole, south pole. They exert a force onto other objects. They exert a push or a pull onto objects that are made of iron or contain iron or are magnets. And they are also surrounded by a magnetic field, which is diagrammed here with these lines called magnetic field lines. When you look at a diagram for a magnet and you see the magnetic field lines, the closer together all these magnetic field lines are, the stronger the magnetic attraction or magnetic pull would be. So if we had a diagram that had additional magnetic field lines in here that were made all these lines closer, because we've got more lines in the same amount of space, that would indicate that the magnet is strongest. Are stronger, I should say. Notice that the magnetic fields are closer at the edges, at the poles, than they are in the middle. This is because the poles of a magnet are stronger than the center of a magnet. Now, if we were to take a magnet and sprinkle filings of iron, just little pieces of iron over top of the magnet, we would get something that looks like this, where lots of iron would collect at the poles because that's where the magnet is strongest, and you can actually see the magnetic field lines in all the pieces of iron, all the sprinklings of iron that we laid over top of the magnet. And then you can see, if you get really far away, that there's some iron that looks like it's pretty much unaffected by the magnet. These would be outside of the magnetic field of the magnet. So every magnet, the magnetic field is limited in terms of how far it is and how much it attracts, depending on how strong the magnet is. Now, there are 2 types of magnets. There are temporary magnets. These are magnets that are easy to magnetize, but they don't hold their magnetic properties very well. And then there are permanent magnets, which are substances that are very difficult to magnetize, but stay a magnet very, very well, essentially permanently. So some temporary magnets are things like the magnetic strip on a key card at a hotel or a gift card, and other types here called electromagnets. If I held up a paperclip against a permanent magnet, I could turn the paperclip into a temporary magnet. But then we can demagnetize these pretty easily. We can strike the magnet, like drop it, we can hit it, or we can increase the temperature, and all these things, any one of those 3 things, striking it, dropping it, or increasing the temperature of the magnet, will cause those domains to become unaligned, and therefore the magnet will lose its magnetic properties. Permanent magnets are very difficult to magnetize, and they retain their properties very well, so dropping it, striking it, increasing the temperature is probably not enough to demagnetize it. You'd have to melt it into just liquid metal. You have to increase the temperature that much and then reform it in order to knock those domains out of alignment. Now, the magnetic field, something to be aware of is that there's a real common relationship here between electricity and magnetism, in that opposites attract. So the south end of a magnet is attracted to the north end of another magnet. Or two south ends, they would repel each other. Two north ends, they would repel each other because likes repel. So we know, with just like with electricity, opposites attract, but likes repel. Now, we can take our knowledge of the similarities between electricity and magnetism, and we can talk about this concept called electromagnetic induction. This is the process of creating an electrical current, specifically an alternating current, by moving a magnetic field or changing a magnetic field. So like this wire off of this device here, this would be a hand crank. This wire is close to the north field, the north end of a magnet, and as we rotate it around, now it's close to the south end of another magnet. And in doing that, we can cause electrons to flow along this metal wire. And here's really how it works. The south end of a magnet attracts electrons. So as the south end of a magnet moves, the electrons move to stay as close as possible. Well, if electrons are attracted to the south end of a magnet, they're repelled by the north end. So as this magnet rotates around in this direction, this is going to be like rotating at a smooth speed, rotating around in a constant direction like that. So as that happens, the north end comes up, and then the north end repels the electrons, so they're being pushed back this way. But the north end continues to move. So as it continues to rotate around, all of a sudden, it's so close to the electrons that some of the electrons are getting pushed in both directions. And then the magnet continues to spin, and now the north end's over here pushing the electrons back in this direction. So initially what we have at the top is that electrons flow in this direction, and then at the bottom now they're flowing in this direction, so we're alternating the direction that those electrons flow. This is alternating current, just by moving a magnet around and changing the magnetic field. Now we can do kind of the opposite. We can take electricity flowing through a circuit through these loops, which we call, this whole set of loops is called a solenoid, and that creates a magnetic field. So we can take electricity and create a magnet from that electricity. Now this solenoid, if we take this solenoid and wrap it around an iron core like a nail, we can create something called an electromagnet. Electromagnets are awesome because we can turn them on and make them magnets, and we can turn them off and have them stop being magnets. It's really, really convenient. And they can also be incredibly, incredibly strong, lifting thousands and thousands and thousands of pounds. So if you go to like a recycling center, you'll see that they take all the metal that you toss in the recycling bin, it all gets shredded up in these little tiny fine pieces, like almost like a dust or a powder. But that's mixed different metals like steel, which contains iron, and aluminum, which does not contain iron. And we know that iron is attracted to a magnet, but aluminum is not. So we can drop this great big metal tub here, which is part of our electromagnet, but it's turned off. So it's not a magnet. We can drop it down into this big mound of various metals, turn on the electromagnet, and when we pull it away, the iron will stick to the magnet, but the aluminum will be left behind. Then we can move this magnet to a totally different location. Over here, we can turn off the magnet, and then all the iron would fall off when we turned off the current, because we wouldn't have a magnet anymore. We've demagnetized that piece of metal, so all the iron falls off. Bring the magnet back over, drop it into this great big mound of metal again, turn on the electricity. We've got a magnet, the iron sticks to it, move it over, turn off the magnet, all the iron falls off, and so on. So it allows us to move things and sort iron out from other metals pretty easily, or in the event of some sort of a disaster, we can move cars because the magnets can be so strong. So electromagnets are really awesome. Now there are 4 things that we can do to make electromagnets stronger. And these 4 things are: we can increase the number of loops in the solenoid. So instead of only having 3 or 4 or 5 loops, maybe we want to have 50,000 loops, and now we've got a much stronger electromagnet. We can also increase the size of the iron. So instead of having a little nail like this, we can have a great big chunk of metal like this here, and that would give us a stronger electromagnet. We can also increase the amount of current flowing through the electricity. So instead of using a single cell like this, you can use large amounts of electricity, lots more current, so that we get a stronger electromagnet. The last thing we can do is use thicker wires. Increase the diameter of the wire that makes up the solenoid, and that will also give us a stronger electromagnet. So we can do any one of these 4 things, or any combination. We can do 3 of them or 4 of them to get stronger and stronger electromagnets. This is why we can get electromagnets that are super, super strong. Now, we also, using the relationship between electricity and magnetism, we can make a device called a generator. And we looked at this hand crank in a picture earlier in the video. where electricity flows along this this wire here in one direction, then back, and one direction and back, depending on whether it's closer to the north end or the south end. This would be like a hand crank generator, which would be really small, produce just a little bit of alternating current, but it does produce current. You might have something like this called a portable, just a portable generator. This would be produce enough current to run, a couple of small household items off of kind of an emergency generator in the event that like power goes out. I have one of these, so that if power goes out at my house, I can keep my refrigerator operating so that all the food doesn't go bad. But it's not enough to run much, too much more on, depending on the generator itself. Now there are some great big, huge generators like this that would be like the size of a bus or at least a large SUV, and a power station where your electricity is being created would have lots of generators. Multiple. This place has 4 here, and just this one area. There's probably a whole bunch elsewhere, and these can output hundreds of thousands of volts of electricity. That can be enough electricity to power huge buildings or towns or cities. So a generator is just any device that takes kinetic energy movement and really movement of position of either the magnets or the wire in relation to the magnets. And so it takes that kinetic energy and converts it into electrical energy. Now we can do the exact opposite, and a device that does the exact opposite is called a motor. And a motor takes electrical current flowing into the motor and causes magnets to spin around, and it causes like this rod, which would be an axle, to spin. And if you had fan blades on the end of that rod, now you've got a fan spinning. So this is like a basic electric motor that you would have in a fan like this. We can also this is like a gas motor in a car does the same thing. It's just it takes gasoline burning is what causes the electricity to first be created from heat. So we have a generator that's producing electricity. That electricity flows through and causes movement, kinetic energy, and then you would have a wheel on the end of the motor so that the motor spins. So motors do the exact opposite of generators. Generators take kinetic energy and convert it to electrical energy, where a motor takes electrical energy and converts it to kinetic energy. So in that sense, they're kind of the exact opposites. Now, when we talked about generators, we looked at this guy, like huge, hundreds and hundreds of thousands of volts that might be sent out from a generator, where like a power plant where your electricity would be coming from. Well, if that much electricity got to your house, you'd be in trouble. All your electronic devices would be fried. They wouldn't be able to handle that much electricity. So we have this device called a transformer that allows us to decrease or increase voltage depending on what direction the electricity is flowing through the transformer. So you got this big, piece of metal here called a magnetic flux, and one side you have a lot of coils on a solenoid wrapped around. The other side is only a few coils wrapped around in a solenoid. So as electricity flows in this direction here, you've got a decrease in voltage. So hundreds of thousands of volts coming through your transformers and decreasing that down. You would have like tons and tons and tons of transformers between a power plant and your house, but ultimately you're taking what might be 500,000 volts output from a power plant and getting that down to 120 volts at your home, so that your electronic devices can all function properly. And then electricity that leaves your house would go through transformers in the opposite direction and would increase in voltage. So you would have 120 volts leaving your house and getting up to hundreds of thousands of volts back at a power plant. So a transformer is a device that allows us to do that. And if you ever looked up on the big wooden poles that hold electrical lines, you might see a tub like this. This is an example of a transformer. Looks like a great big bucket. Now, some other things to talk about real quick as it relates to magnetism is Earth itself is basically a great big magnet. With the North Pole, what you think of as the North Pole, the geographic north, the top of the planet, that is actually the magnetic South Pole. And the geographic South Pole is actually the magnetic North Pole. Now, this hasn't always been the case. This has actually flipped, and scientists know this because they've looked at the magnetic portions of rocks, sedimentary rocks, and they can see that the materials were pulled originally in one direction and pulled back in other directions. So we know that this has changed. If this ever changed again, we don't really know how that would affect us and our electronic devices and what would happen to Earth while this is going through the process of changing. So that's something that has some scientists curious and concerned. To be honest, we expect it to happen, but who knows when? It could be in a year. It could be in 10,000 years. Who knows? But Earth itself is basically a great big magnet, and this is because in the center of Earth there's what's called the inner core, is a solid mass of essentially iron with maybe some nickel. And then around that is liquid iron that's constantly flowing in a circular motion, and that's what causes this magnetic field. Now, this magnetic field is what allows a compass to work. The north end of a compass points north because it's attracted to the magnetic south pole. So the north pole of the magnet would point this way because it's attracted to the south pole of Earth itself. So that's what allows a compass to function if you've ever actually used one. Now, the other thing that these magnetic poles do for us is they protect us from solar radiation. Radiation is the transfer of energy in electromagnetic waves, hopefully electromagnetic waves, and electromagnetic field. We see a relation there, and the size and strength of the electromagnetic field is largely related to how much iron is moving around in the core of Earth, as well as the speed at which the planet is moving. And it's this electromagnetic field that protects us so that our planet doesn't cook. It's one of the reasons why, even if you could breathe on Mars, if Mars had an atmosphere, if you went and just stood outside on Mars, your skin would burn right away. I mean, immediately, because there's not the electromagnetic field protecting the planet the same way that Earth has. And it's an important factor as scientists look elsewhere and observe other planets to see if there are other planets that might be able to support life, or maybe even could support human life if we could go colonize another planet. It's important that we look at planets that have a strong enough electromagnetic field to protect from solar radiation. So Earth itself is really just a great big magnet, and that has some benefits to us, like the ability to navigate using a compass and the ability to protect us from solar radiation. So that's our video on magnetism. If you have questions, email me or stop in and see me to get some stuff clarified. And hopefully the electricity and magnetism unit you found to be interesting. All right, have a good night.